In this video, we will somewhat derive to you the understanding of the Euler's forward method, alright, in terms of really we derive to you, alright, the derivations. Alright, and before we start, we'll just start off with something that is familiar to you, which is the continuous signal integration. Alright, this et over here is a certain function. Alright, if you were to integrate the certain functions, you'll get the area under the curve. Alright, so to be more exact, alright, your et is this particular curvature, et, alright, and the area under the curve is actually this one, correct? And we can actually rewrite our et as dt over dt. Okay, so what do I mean by this? If let's say our t is equals to tk minus 1, okay, for example, so in graphically way, this is tk, this is tk minus 1. Alright, this is a time at certain value, So if time at maybe 3, then 3 minus 2 is actually 2. So this point is 2, this is 3. Alright, then this is 1, then this is 0. So this is the time domain. Okay, so I'm just trying to write in terms of this manner first. Okay, and therefore if I were to take this one, tk minus tk minus 1, which is this length, what you're left with is actually this thing, the difference between them. Alright, and we call this thing the t. Okay, so the changes in t dt, I should say that dt is tk minus 1, which is this one, correct? And if you were to divide by dt, alright, such that your dt is very small, you're gonna move this tk minus 1 more closer to your dt. So in other words, you're starting to go more and more closer to your tk, such that it is very, very infinitesimally small, such that the tk and tk minus 1 is somewhere just very, very, very near each other. Alright, so therefore this is the point. And then if you were to differentiate each of this point, alright, you're gonna differentiate every of these 2 points, you're starting to plot out this curve, right? You'll start to plot out this whole full curve. Alright, so therefore this thing is by legit your et, because your et is this curve. So you are differentiating each of this point by point all the way, and then you form this particular curve. Then if you were to integrate, you'll just get back this area under the curve. Okay, and therefore with the same understanding, we're going to derive the digital signal based on this stuff. Okay, so therefore how can we do? What can we do? So therefore I'm going to introduce you with this formula, and this is somewhat a logical one. Alright, and I'll explain to you now. Is that your previous output plus your current input with regards to t, which is the difference between different time domain, alright, multiplied by your input will give you your new output. Alright, u is actually called the output, e is called the input. So input k, ek is your current input, uk is your current output, k minus 1 is your previous output. Okay, so how do I start? I'll just start with the first point first. Alright, in this case, I will call this our tk minus 1. Okay, and I will call this particular point tk. Alright, so over here, if you were to apply this formula, okay, your uk minus 1 is what? Is actually 0. It's because we're starting at the origin. Alright, we just started out. Alright, so we just started out with this particular thing. So uk minus 1 is simply 0 for our case. Alright, because we have just started out trying to plot out this curve. So this is the starting point. So starting point, we have no previous information. Alright, if you're talking about previous information, then we'll talk about these informations. But however, we are starting from time equals to 0. Alright, so therefore and when talking about time equals to 0, you're going to talk about a causal system, I think. Forget. But anyway, in the next video, we'll talk about that. Alright, but nonetheless, your tek, alright, you remember your t is actually equals to tk minus 1. Alright, so So therefore I will just take tk minus tk minus 1 is actually at its origin, so I didn't do anything. So this is actually simply tk. So this length is actually tk, or this length is actually t lah. Okay, and if I were to multiply by ek, okay, so this thing over here I know is t, and if I were to multiply an input, impulse input at ek, so at k, ek means at k you shoot out impulse input over here. Okay, so if you're talking about this is actually ek minus 1. Alright, it's the previous input with previous impulse. Alright, but now we are only talking about t multiplied by ek, which is our current input at this point at tk. Correct, so we will shoot up at this thing. Alright, so this is your ek. Okay, so t times ek will give you this rectangular shape over here. Alright, you see, so you have formed the first signal. Alright, let me touch up a little bit. So you have formed this new signal, okay, at this between these 2 points. Okay, and you will know that later on we can actually form the other next signals all together. Alright, so this signal over here is your uk, okay, at this thing. Alright, but next maybe I should, alright, because my point is pretty close, is that this thing is pretty big. I want to actually shorten this. Alright, because I have no space lah. Okay, so my uk, alright, this thing over here is still your t, this is your ek lah. Okay, and this thing over, this whole signal over here is your uk. Okay, so this uk, with reference to new signal, have happened that I have a new signal over here, new point. Alright, then this uk over here will becomes the previous, so this thing over here becomes uk minus 1 already. Alright, if you are talking about this reference frame with regards to these 2 points, alright, then your previous 2 points all over here, alright, this maybe the green points becomes your previous output already. Correct, so just now we have calculated is this one, right? This is considered uk. Alright, but in the next time step, alright, which is at this point, alright, this thing over here becomes your o input, your o output already. Alright, so previously what we have been calculating is to calculate an output which is uk, but with reference to the next one, this becomes uk minus 1 because it's a previous stuff already. Okay, hopefully this is pretty clear for you. If you don't understand, you just click back a few seconds and you rewatch and repeat until you understand what I mean. And therefore, since we know that this thing over here is considered uk minus 1, okay, then I can just simply remove this thing, alright, because I want to redefine my new step. Okay, so this thing over here is our uk minus 1 already, our previous output. Alright, so let's talk about the new system. Alright, let's say we have a new system. Alright, so a new system will redefine, and in this case I'll define this as tk minus 1. Alright, previously we say that this point is tk minus 1. Now because of a new time step, this O1 becomes tk minus 1. In other words, this one will becomes tk minus 2 lah. Okay, so this tk minus 1 and this is actually tk. Correct, so now I will take tk, which is at this point. Maybe I should use a different brighter color, thicker lines also. So this thing is tk, minus away tk minus 1, you'll get the difference. Alright, so this thing over here is your new t. Okay, and when you multiply with a ek, so I multiply with ek, I should have said ek is this line over here, because ek tells you that you're taking impulse at k, or at time k. If it's ek minus 1, then you're taking impulse at this point. Alright, so be careful of that. Alright, so ek is only talking about this impulse. So if let's say you have t times ek, then you're going to form a new rectangle over here. So this is your new uk. Or in other words, your blue color one plus this red color one give you your output. So your full system over here, you see, is your uk already. Okay, so you see that so you have mixed your previous information within your current output already. You see. So therefore, hopefully you understand. So therefore this full system now, with reference to the next time step, alright, with regards to the next step or next point, alright, this whole thing over here is now your new uk minus 1. Alright, and you're going to redefine at this point as tk minus 1, and you redefine this point as tk, okay, or in other words this point as tk. Alright, so the difference, so if you take the difference between them, tk minus 1, you'll get t. Alright, because this is just the definitions. Alright, tk minus 1 is your t, don't forget. Alright, so therefore this is your t. And then if you were to multiply a impulse at k, alright, so this is called ek. Correct? If it impulse at ek minus 1, then it is impulse at this point. Alright, so be careful of that. Alright, so t times ek, you'll get this rectangular. Alright, so this rectangular, this tek is your this point plus your previous input, your previous output, which are all this. Alright, this one is all these things. Alright, so this thing, which is this thing plus these things, will give you your full system over here, area under the curve. So you keep on loop, you form the full curve all along. Alright, which is area under the curve in the digital domain. Alright, so I hope that this is pretty clear for you up to this point. Alright, and therefore we can know that this method is this equation works, right? Because we have used the example to explain to you, right? So therefore, using this, then we can derive our forward Euler's formula. So what I can do is that uk minus 1 is equals to tek, correct? So I'll just bring this one to the other side lah, okay? Next, alright, I bring this t downwards. Alright, what I have is this one, okay? And this is your forward Euler's formula. And after looking at things, I realized that I've written the wrong formula. Damn it, I lazy to do already, okay? So I'll just simply change from here, since you already understand everything. Just that this is ek minus 1. So instead of multiplying t times ek, which is at this line, alright, so instead of that line, alright, we'll multiply with ek minus 1. Alright, so t times ek minus 1. Okay, so in other words, we are talking about t times this rectangle. Okay, t times this rectangle. Alright, instead of t times this one. Alright, this thing is ek, this line is ek minus 1. Okay, so what I've been doing is keep on multiplying ek, but in fact the equation is actually ek minus 1. Alright, so this is just a small thing, but you will not change your perception of what we have learned. Alright, it's just simply only this part. ek minus 1, ek, you change to ek minus 1. Alright, so we multiply with ek minus 1, that's all. Alright, the same thing goes for output, previous output and things like that are still the same meaning. Just this part, be careful of that. Alright, so therefore I'm gonna rearrange the stuff. Alright, I'm gonna rearrange the stuff so that at least you fully understand what I will do. So the ek minus 1, I'll apply it for the rest of the equation that I've calculated. So hopefully I can rewrite as this thing. Alright. Okay, so therefore this thing over here is somewhat the same as this, but a little bit different, right? So because this is actually k, this is k minus 1, this is k plus 1, this is k. Alright, it's just a time step difference. So if I were to plus a time step for here, I'll have uk plus 1 minus, if I were to plus a time step for here, I'll have become uk already, right? uk minus 1 plus 1 is actually, minus 1 plus 1 is actually 0, right? So you'll just get back uk, okay? Over here, ek minus 1, I will plus 1, I will have ek, okay, over t, okay? So this thing over here is this thing over here, alright, it's the same, just instead of u, they write as x, it's the same thing, alright? But over here, ek, why they write as u dot k? Ek, if you think about it, ek is equals to uk plus 1. Is it? Right, uk plus 2. Sorry. Now you're like, what the hell is going on already? Are you trying to cheat my feeling or what? And yes, because I am wrong. Yeah, I'm learning lah, okay? So anyway, so your ek is equals to uk plus 2 over t1. Alright, previously is t is tk plus 1 minus tk. Alright, if you think about it, just now our t is equals to tk minus 1. Alright, but however over here we say that the k, alright, we can change to k plus 1. Alright, while the k minus 1 I can change to k. So likewise, the t over here at first was tk minus 1. So if I were to do k, I will change to k plus 1. Over here, this k, I also have to change to k plus 1, right? Which is over here. So the k minus 1, I also change to tk, which is the same follow suit. So this t belongs to this one, okay? So it's equals to ek, where your ek is equals to uk plus 2 divided by t1. Alright, this t1 is actually this t1 over here. Okay, while this t is over here. Okay, so what it means is that you take your uk plus 1, this is uk plus 1 minus uk, alright, you're getting this area, correct? So this area divided by t will give you your ek minus your ek over here. Alright, this is ek. This whole line is ek. Alright, so this is ek, this is ek minus 1. Over here, this is ek plus 1. Okay, but anyway, yeah, so this is ek lah. Alright, so nonetheless, your ek, alright, this line over here can be represented because if you think about it, this is the new area you're talking. Alright, so this ek is equals to your uk plus 2. Alright, your uk plus 2 is actually I'm actually going to more and more complicated stuff. This means that I'm not fully understand things yet. Damn it. But anyway, I'll leave you to think about it. Alright, and I think that's it lah. Okay, so the key concept over here is just that eventually you derive this thing. Alright, by far this is your forward Euler's formula, but in order to prove that your ek is equals to this one, I suck. Alright, I suck. So leave it to you. Alright, in the future if you need it, then you continue to own self derive. So see you soon.